Okay, this is number 19 from the Chapter 12 review. Sorry about the amazing quality that we have here. Okay, so here is the question. It is long. I'm not going to read it word for word. Key things though. Let's see if I can grab the mouse to point. We've got two throwers. The mean distance thrown by Ian in the past year was 60.33 meters, standard deviation of 1.95. So there's our stats for him. I'm gonna jot that down. Again, sorry about the video quality, but at least you have a video. 60.33, standard deviation of 1.95. Okay, part A. In the past year, 80% of Ian's throws have been longer than, greater than X meters. Find X. So we've got this normally distributed data, so it's fitting on this bell curve. Our average is the 60.33. Standard deviations are this 1.95. 80% of his throws have been longer than X meters. So 80% is greater than. 80% is on the right. So here's 50%. I know the one standard deviation way would give me 34% on this side. So it won't quite be up to that. Like if these are my standard deviations, then I'm looking in here and greater. That area is 0.8. Again, got 0.8 because half of it is 50% or 0.5. And there's another 34% in here. So 34 plus that 50 would be bigger than 80. So there is an X coordinate that goes with that 0.8. Find X correct to two decimal places. Anytime we're given an area and asked about something on the x-axis, that could be an x coordinate, that could be the average, that could be the standard deviation. We use inverse norm. So inverse norm on the calculator, again, I have a classic calculator here, is in the distribution menu. So that's still going to be true for you. Option 3 for inverse norm, I think that's consistent on the new calculators too. Here's where it's going to look different. So on your calculators, it's going to say area, and we put a number in there. It's going to say average. It's going to say standard deviation. And then if it's fancy enough, you'll have left, center, right. Okay, that area is the shaded area. So on your calculator, you're going to be putting in a 0.8 here. Average and standard deviation. We know both of those, so it is okay to put both of them in. What that's doing is then your calculator will find the z-score for you and then complete the z-score formula, solving it immediately for x. So it saves you a step if what you're looking for is that x coordinate. So we can type in the 60.33 and the 1.95. Your calculator, again, has left, center, right. We shaded on the right of that x coordinate, so you would make sure that right is highlighted. My calculator is old, so it can only do left. So for me, the area that I have on the left is 0.2. So you can completely ignore these directions or this screen because your calculator will be fancier. And let's hope that that is the right order. 58.69, I think. It said correct to two decimal places. So that X value, 58.69. Let's see, does that make sense? So with the shading, I was within one standard deviation. One standard deviation away is almost 2. So if I were to subtract 2 from about 60, I'd be at 58-ish. So I know it should be a little bit bigger, a little bit to the right of 58-ish, and that's what I have here. So trying to do a reasonable check. 58.69. I don't know that they were marking points for units. The x-axis is a distance, so that would be in meters. Okay, taking a look at part B. In the past year, 80% of Carl's throws have been longer than a certain amount. If his average is 59.39, find the standard deviation correct to two decimal places. Okay, different guy. This one is Carl. And you don't have to do the picture, but it helps me, oops, that's terrible. Helps me figure out what's going on, assuming I can kind of draw it. Okay, 80% of Carl's throws have been longer than 56.52. Actually, because I drew that so poorly, that's going to be the 56.52. This is going to be my average. So 80%, just like this guy, 0.8 on the right, longer than 56.52. So that's that x coordinate. The average, which is this line, is 59.39. Find standard deviation. Okay, I'm given an area, so I'm using inverse norm. So inverse norm again will have area equals, on your calculator, we're still using that 0.8 on the right. We don't know, because it's a different person, we don't know both of these. Actually, what we're looking for is one of them. That means you leave the default settings in. So your average is 0, standard deviation is 1. Your calculator has the option of being on the right, so we'd make sure that's highlighted and hit enter. My calculator is old. So let's see, on that area for the left for me, 0.2, and that's all I'm doing. So what this gives me, and what this will give you, is the z-score. So z-score, if you have the standard values in, or excuse me, inverse norm, if you have the standard values in, will tell you z-score. So x minus the average over standard deviation. So that z is equal to 0.842-ish. And when I'm doing stuff with this, I'm going to go back to the unrounded number, so I'm not rounding multiple times within a problem and risking being off, particularly because they ask me to be correct to 2 decimal places. So 0.842-ish equal to the x coordinate. Hey, we do know that. That's the 56.52 minus the average, 59.39. Oh, and I didn't jot this. Sorry, this should be negative and negative. 59.39 divided by the thing that we are solving for. I think this is similar to what we did in number 3. So I can multiply both sides by sigma, so negative 0.842 sigma equal to the difference between those two. Let's see, 56.52 minus 59, oops, 0.39. So I'm getting negative 2.87. Solving for sigma, I'm going to divide both sides by that standard deviation. So negative divided by negative 0.84. And then it was really 162.12335. Like I'm just, whoa. I swear I didn't type that. I typed the actual thing. Well, that's unhelpful. Well, that's what we would do. Negative 2.87. But now I don't have that actual number. Dang it. Negative 0.84. It was like 1.6 blah, blah, blah. Okay, so approximately 3.41 is what I'm getting, but if you use the unrounded, it might still round to this, or you'll get something more accurate. So that is part B, hopefully. Part C is tricky. Here's where the sneakiness comes in with IB. Carl's throws have an average of 59.5. Just writing this down as I go. And a standard deviation of 3. So new year, new stats. Ian has actually the same stats. 1.95, yep, so Ian is the same as up above. All right. In a competition, must have at least one throw 65 meters or more in the first round to qualify for the final round. Each athlete is allowed 3 throws in the final round. Determine which of these 2 athletes is more likely to qualify for the final on their first throw. So it doesn't really matter that they get 3 throws. I only care about the first throw here. So that's kind of extra information just to throw you off. Throw you off. Ha. Okay, can you tell? It's 9 p.m. I am getting a little punchy. Okay, so what happened with this? Well, it's no longer talking about a normal distribution, really. It's talking about we made it into the finals or we did not. This is flipping to a binomial situation. Those are often really tricky to catch. So with the binomial situation, so here's Ian's data, here's Carl's data. What we need is the N, the P, and the X amounts for binomial. We want to figure out the number of trials that we have here. Number of trials for Ian and for Carl. So I'll write these NPXs. Just in case they're different, for the different stats that are here. Determine which of these 2 athletes is more likely to qualify for the final on their first throw. Okay, so we're only doing 1 throw. That's all I care about. So my number of trials is 1. Probability of success. That's where this stuff is coming in. In order to be considered successful, my bell curves are getting worse. Here's my average. We have to throw, I think it was greater than 65 meters. So 65 meters is somewhere over here. That's going to be an X coordinate, and we need this amount. That is, for each athlete, the probability of success. So Ian's going to have a value for P, and Carl's going to have a different value for P. Their individual probability that they'll throw farther than 65 meters. So I need to figure out what is that percentage. Well, that's kind of repeating some of the things that we've done earlier in the review, where I know that it's a normal distribution and I want everything greater than 65. So we're really looking for the probability in a normal distribution that X is greater than 65 meters for both these guys. That comes from the normal distribution. So normal CDF with lower of 65 and an upper value of something more than 3 standard deviations away. So I'll put in just a ridiculously large number, 1,000 meters. We're not throwing a javelin or whatever this is, a kilometer. The average will be unique to the person, and the standard deviation will be unique to the person. So on the calculator, we would go to the distribution menu and go for norm CDF. You would type those values in, lower, upper, I'll do Ian, 60.33 for his average, standard deviation of 1.95. So I am getting 0.8%, 0.00831. So probability of success, 0.00831. Repeating that same kind of thing for the other guy. Again, it's got to be larger than 65. That person's average is 59.5. with a standard deviation of 3. So 0.0333 or 334. That's this guy's probability of success. 0.03337, yada yada. We want them to hit that on their one throw. Like they need to get exactly 1. What's the chance that that's going to happen? So looking at the percentages, like Carl's much more likely for this to happen. he is more likely to qualify on the first throw because this probability is higher. How I can justify that is by doing a normal distribution, or excuse me, binomial distribution, binom PDF, where we're typing in our n, p, and x values. And we wind up getting these exact same things because they're the expected values. So those are our probabilities. So Carl is much more likely at 3% as opposed to 0.8% of that happening. Part 2, find the probability that both athletes qualify for the final. Okay, so that means that at least one of their throws needs to be, at least one of their 3 throws needs to be greater than 65. So this is the chance of that happening. So in n trials, with a probability, I'll write down en, of 0.00831-ish, so 3 throws, we need the probability of x being greater than or equal to 1. Again, he could qualify on the first, second, or third, or all 3. Really, the only case we don't want is the 0 case, where he doesn't hit it. So if we don't want this one, 1 minus that case will give us what we actually do want. It'll give us the greater than or equal to 1. Okay, typing that into my calculator, I have 0.0247-ish. So that's the chance that, I think this was Ian's data, that's the chance that Ian will qualify in the first 3 throws. So that's the chance that he'll qualify. We can do the same thing for Carl. So in 3 tries, his probability of success was greater. It was that 0.3337-ish, blah, 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 blah. And again, it would be okay if 1 throw qualified, or 2, or 3. So what's the case we don't want? We don't want the exactly 0 case. This would be him not qualifying. So 1 minus what we don't want will leave us with what we do want. So give me a second to try to type that in and hope that this calculator does not crash again. 0.03337. So I have approximately 0.0968. It's about 9% chance that Carl will qualify, 2% chance that Ian will qualify. But what is part, I think this is C-double-I ask? It wants the chance that both of them qualify, I think. I think it is both. Yeah, both athletes qualify. So we need Ian qualifying and we need Carl qualifying. Anytime I say and, I'm multiplying. So I'm multiplying these 2 percentages together, 0.0247 multiplied by the 9-ish% that we just got. And this is what I'm seeing on my calculator. I can see nothing. So that's what we would do, is we'd multiply those together, and whatever we get, that's going to be the probability. I did look at the answer key for this one, the work solutions, and let's see, when we multiply those 2 values together, it looks like we should get 0.00239 approximately. Now, also looking at this work solutions, I don't know what they're doing in part 1 up here because the question very clearly states they're qualifying on the first throw, so we don't care about the other 2. They're taking the other ones into account here. So they've got a less than 65, but it says that it's greater than. So ignore this. This is not accurate. We have these smaller percentages because that makes sense. I mean, if their average is 59 here and they've got a hit larger than 65, with a standard deviation of 3, that's a slim chance of that happening. There's very little area over here. It's not 99% likely, as they've stated. It's that 0.008% likely, or 0.8% likely.